This video is the review for the Sinclair Exam 3 for statistics. It says a medical researcher treats 400 subjects with a high cholesterol with a new drug. The average decrease in cholesterol is X bar equals 90 after 2 months of taking the drug. Assume that the decrease in cholesterol after 2 months follows a normal distribution with an unknown mean and a standard deviation of 30. Okay, find the 95% confidence interval for mu. All right, so since we said unknown mean, the standard deviation is known, we can use a z-curve. Okay, so standard deviation with sigma is going to be a z-curve. See if I can get that to focus better. All right, so I'm going to do a z-test, okay, on mean. Okay, all right, next. So run the app. I'm going to go down to confidence interval. All right, and I'm going to do a z-test on mean. All right, so our n was 400. Our decrease was 90. Okay, our standard deviation was 30. Confidence level in this case is 95, so 0.95. And what they're telling us here, first I need to record the standard deviation of X bar is 1.5. Again, that comes from the 30 divided by the square root of 400, which is 20. Okay, I need to identify the z-value, which is 1.96. I need to also describe the error, and so the error, which is the multiplication of these two values, gives me 2.94, and that's what we add and subtract from the mean of 90. Okay, so that gave me an interval of 87.06 to 92.94. All right, so we would say in language, we are 95% confident that the true mean change in cholesterol is captured by the interval from 87 to 93. All right, which of the following would produce a confidence interval with a smaller margin of error than the 95% confidence interval you computed above? All right, so we want the 87 to 92 to become closer to 90. All right, so give the drug to only 100 subjects rather than 400. Okay, no. If we want to have a tighter window, we want to increase the sample size, not decrease it. Give the drug to 500 subjects, yes, that would decrease it. Compute a 99% interval rather than a 90, no. So that would not work. If you want to have a tighter window, you would decrease the confidence level. Increasing it would widen this, so we have to be wider to accompany 99%. All right, so the only one that was a yes was 2. All right, use the following to answer questions 2 and 3. You measure lifetime of random sample of 64 tires of a certain brand. The sample mean is X bar equals 50 months. And suppose that the lifetimes for tires of this brand allow for a normal distribution with unknown mean and standard deviation of 5. So again, they're telling us that we know the standard deviation, therefore we can use a z-curve. A 95% confidence interval is what? Okay, so this is a z-test on mean. Okay, so I need to calculate the, let's do it again. All right, so from basic stats, confidence interval, okay, z-test on mean. They said we're testing 64 tires. Okay, our X bar was 50 months. All right, population standard deviation was 5 months. So how long a tire lasts? Average 50, standard deviation of 5. Confidence level, they said it was 95. So here's our values we're going to record. Okay, so we have a z-value of 1.96. Again, that is just standard for a 95% confidence interval. Our standard deviation of X bar, okay, again, that is the standard deviation divided by the square root of n. That is 0.625. If you multiply these two together, you end up with the error. The error here is 1.2 2. All right, now, see if that helps. There we go. Okay, so now that gave us an interval of 48.78 to 51.22. All right, got it. Okay, so what that means is we are 95% confident that the true life of the tires in months is captured by the mean from 48.78 to 51.22. All right, next, suppose that I had measured the lifetime of a random sample of 100 tires rather than 64. Which of the following statements is true? So if we increase the sample size, standard deviation goes down, therefore error goes down, therefore the window becomes tighter or more narrow. Okay, the margin of error of our 95% confidence interval would increase. So error would go down. That is not true. Okay, the margin of error would decrease. Yes. Okay, the margin of error for 95% confidence would stay the same. No. Okay, and standard deviation would decrease. No. Okay, standard deviation and standard deviation of x bar are different measures. Okay, so the only one that would actually be true here is B. All right, to assess the accuracy of a laboratory scale, a standard weight known to weigh 1 gram is repeatedly weighed a total of n times. The mean x bar of the weights is computed. Okay, so we're looking at means. Suppose the scale readings are normally distributed with a mean m and a standard deviation of 0.01. How large should n be so that a 95% confidence interval has a margin of error of 0.0001? Okay, so this is the unknown sample size question, which means we go with the error formula. So it's standard, we have stat plus or minus the z or t, in this case z, multiplied by the standard deviation of the statistic. Okay, this piece right here is the error. And they told us that we want that amount to be this. All right, so the error equals our z multiplied by the standard deviation of x bar. Okay, now error is known to be 0.0001. We're doing a 95% confidence interval with a z value, so that's 1.96. Okay, now the standard deviation of x bar is the standard deviation divided by the square root of n. Okay, they told us that the standard deviation is 0.01 divided by the square root of n. All right, at this point, I'm just going to multiply these top two together. So 0.0001 equals, and when I multiply that by 0.01, I have 0.0196 over square root of n. Typically, I treat these like a proportion. So I cross multiply and divide. So now I have 0.0051 equals the square root of n, so I square the both sides. I did that backwards, my bad. Fixing it now. Okay, 0.0196 divided by 0.0001 gives me 196. There we go. Okay, so now when I square both sides, I end up at 38,416. Keep in mind, if you get a decimal here, like even if it's a 0.1 or 0.05, you always round up on this value right there. All right. Okay, in their advertisements, the manufacturer of a certain brand of breakfast cereal would like to claim that eating their oatmeal for breakfast daily will produce a mean decrease of cholesterol of more than 10 points in 1 month for people with cholesterol levels over 200. Okay, In order to determine if this is a valid claim, they hire an independent testing agency which selects 25 people with a cholesterol level over 200 to eat their cereal for breakfast daily for a month. The agency should be testing the null hypothesis that the average is 10 and the alternate hypothesis what? Okay, so they didn't say if it is, we assume that the true value is above it or below it, so we only test against that it is not equal to 10. Okay, so this shows up when the assumption is that their claim is too high. This shows up if the assumption is that their claim is too low. This shows up just to test if their claim is true. This is a two-sided test. This is a less than test, so it is a left tail test, a one-sided test. This is a greater than test, so it is a right tail test, a right-sided test. All right, there we go. Suppose that we are testing the null hypothesis, okay, that the mean is 20, and the alternate hypothesis that it is not 20 for a normal population, standard deviation of 5. The random sample of 25 observations are drawn from a population. We find that the sample mean of these observations, x bar, is 17.6. The p-value is closest to what? Okay, so we have a significance test or hypothesis test. So when we go to the app, okay, we're going to run our hypothesis test, and they said that we know the sigma is 5, okay? So therefore we can do a test on mean, and we can run it as a z-test. So we're going to do a z-test on mean, okay? The null is what? Okay, so the null is 20. The sample mean they said was 17.6. Okay, the standard deviation was 5. Sample size here was 25. Okay, and we're going to run this as a z-test. All right, and we are running this as a not equal to test, so we double the p-value. All right, so in this case, the things we should record here, we have the standard deviation of x bar, which is the standard deviation divided by the square root of the sample size, comes out to 1. Okay. Next, we have a z-value of negative 2.4, and the p-value, in this case, is 0.016. Here we go. Remember, a not equal to test uses the 2 times p-value. A one-sided test would have used the 0.008. Okay, based on the p-value calculated above, what's the conclusion? Okay, so first of all, do we know the alpha level? Okay, so the above conclusion, if the alpha level is 0.05, which we were not told, so that is the default level, okay, then we would reject the null, okay, because the 0.0164 is less than 0.05. So there's less than a 5% chance. So if we reject if there's less than a 5% chance of this happening, and there we go. Let's go over to the meaning of the p-value really quick. All right, so what this is telling us is if the null is true, so if the mean is truly 20, the chance of x bar showing up this far away is only 1%. Okay, so it's a 1.6% chance. So if we're testing at a 5% alpha level, then we would reject anything that's below 5%. This is 1.6%, therefore we reject. All right, the next one. Use this to answer 8 to 12. The survey of study habits and attitudes, psychological test that measures motivation, attitudes, and study habits of college students. Scores range from 0 to 200, follow approximately a normal distribution with mean 110, standard deviation of 20. You suspect that incoming freshmen have a mean mu which is different from 110 because they are often excited yet anxious about entering college. All right, so all we know is that it is different. To verify your suspicion, you test the hypotheses. It is 110, it is not 110. All right, you give the test to 50 students who are incoming freshmen and find their mean score. Okay, the p-value of the test, of the null hypothesis is, so let's just think it through before we answer anything. It is the chance of getting the x bar given that the null is true. So it is the probability, assuming the null is true, that the test statistic will take a value at least as extreme as the one actually observed. That looks really good. The probability assuming the null is false? No. The probability that the null is true? No. Probability that the null is false? No. A. There we go. If you observe a sample mean of 115.35, what is the corresponding p-value? Okay, we can do this. So, again, this is a z-test on mean because we know the standard deviation. Okay, so they told us up here the standard deviation of this test is 20. All right, got it. So when I go to hypothesis test, okay, on the calculator, we are testing a mean. The null was 110, so again, the null is 110. They said our sample was 115.35. The standard deviation of ours was up here at 20. The sample size here, 50. So we had values found all over the place. And we're going to run a z-test. Okay, so we need to record the standard deviation of x bar of 2.82. All right, our z value here is 1.89. Now, this is a two-sided test, okay? So therefore, our p-value, we use the doubled value of 0.058, so 0.06. Got it. All right, now what? Does the p-value support the suspicion that incoming freshmen have a different mean score than the 110 if the significance is 0.05? All right, this is above, so no, we fail to reject. We don't say the null is true or false. We either reject it or we fail to reject it. Fail to reject the null because 0.06 is greater than 0.05. All right. Doesn't mean that that one is true. It just means we don't have evidence to reject it. All right. Suppose that you observed sample mean of x bar equals 150. This is like the same one, but based on a sample of 100 students, what would the corresponding p-value be? All right, so we're going to run it again. They did tell us that we're using that same information that we just worked with for 11 and 12. Okay, so let's run it again. All right, so I'm going to the hypothesis test. We're testing on a mean. The null mean was 110. The sample mean was 115.35. Okay, the S of x value from that is 20. And they're saying run it now with 100 students as a z-test. Okay, now the p-value now, again, we're using a double test, is 0.007. Okay, so 0.0074. All right, does the p-value support the suspicion that the incoming freshmen have a different mean score of 110 if the significance level is 0.05? Yes. Now we reject null because 0.0074 is less than 0.05. So changing the sample size to 100 drastically changed the results. All right, suppose the time it takes a certain large bank to approve a home loan is normally distributed with a mean mu, standard deviation, so we know the standard deviation. The bank advertises that it approves loans in 5 days on average, but measurements on random sample of 500 loan applications to this bank gave a mean approval 5.3 days. Is this evidence that the mean to approve is actually longer than advertised? To answer this, we have these hypotheses. So it is 5, it's greater than 5. One-sided test, it's a right-tail test. At significance level of 0.01, so we've got a high level of confidence we need to gain. You conclude that what? H of O should be rejected. Okay, let's run it. Okay. So again, because we know the standard deviation, we can run a z-test on mean. So I will write that down again. Z-test on mean. So from here, basic stats, hypothesis test, test on mean. The null mean here was 5. Okay, that's the claim. The X bar came out to 5.3, and it said that they know the standard deviation is 1, and they said this for 500 values. Z-test. Okay, now, they're just asking if we should reject or not, but they might ask something else later, so I'm just going to record the significant things that I need. It's 0.045. The z-value here is 6.71, which is an enormous z-value. It's a one-sided test, so we're going to use the p-value of, and again, it was 9.9 times 10 to the negative 12th, which is definitely less than 0.01. Okay, so we should reject. All right. A radio show conducts a phone-in survey each morning. Listeners are asked to call in with a response to the question of the day. One morning in 2011, listeners were asked if they supported or opposed term limits for members of Congress. 88% of listeners that called in favored term limits. We may safely conclude that there's overwhelming approval from congressional limits among Americans generally. It is unlikely that if Americans were asked their opinion, the results would differ from that obtained in the poll. There is strong evidence that the majority of Americans believe that there should be congressional term limits. Nothing except that a great majority of those with strong enough feelings on the issue to call in are in favor of term limits. D. Got it. Okay, type 1 error is, all right, type 1, null is true, which means type 2, null is false. Okay, and we err, so we find false, which means reject. Okay, null is false, which means we should reject it, but we fail to reject. There's our two types of errors. Okay, so rejecting the null when it is true, accepting the null when it is false. So in this case, the null is true, okay? And we find it false. Rejecting the null when it is true. There we go. Incorrectly specifying the null, incorrectly specifying the alternate. No. Okay, so accepting the null when it is false would be A2. Okay, so A was the type 1, B was the type 2. Use the following to answer 16 to 18. So these are going to be used for multiple questions. All right, an SRS of 18 recent birth records at the local hospital was selected. In the sample, the average birth weight was this, okay, ounces, and the standard deviation was this. All right, so this is in the sample. This is S of X. All right, that's important. So now we've lost our ability to use the Z-curve. Assuming the population of all babies born in this hospital, the birth weights follow a normal distribution with mean mu. All right, the standard error of the mean is what? Okay, the standard error of the mean is the standard deviation of x bar, which is the standard deviation divided by the square root of n. In this case, we're using S of x over the square root of n, which is 6.5 divided by the square root of 18. Okay? So 6.5 divided by the square root of 18 is 1.53. There we go. Okay. Now, next problem. 17. We are interested in a 95% confidence interval for the population mean weight. The margin of error associated with the confidence level is what? All right, we can do this. They're looking for the margin of error. The margin of error, from the calculator, let's just go ahead and find the confidence interval right now. So, program, AP Stats, next menu, confidence interval. Okay, so we're going to do a t-test on mean. The reason we're running a t-test, not a z-test, is because we're working with a sample standard deviation, not the population standard deviation. Okay, now our n was 18. Our x bar came out to 119.6. Standard deviation was 6.5. Confidence level we're running this at is 95. All right, so it's thinking, it's got to calculate the t. All right, so I'm going to write down some of these things that I need. I know the standard deviation of x bar was 1.53. We did that on the last page. The t value is important here. That's 2.1. These two multiply together to create the error. So when I'm writing down the error, I'm really writing down what these two multiply to make. And that is 3.23. The interval is 116.36 to 122.83. Okay, so the error, 3.23, is B. 95% interval for the population is based on this is the mean plus or minus the error, so we need 3.23 right there. Got it. Okay, use the following to answer 19 to 24. All right, so it's all of these plus 1. Special diet is intended to reduce the blood pressure. If diet is effective, the target is to have the average systolic blood pressure of this group below 150. So that's our goal, 150. After 6 months on the diet, an SRS of 28 patients with high blood pressure had an average cholesterol of 143, with standard deviation S equals 21. Is this sufficient evidence that the diet is effective in meeting the target, assuming the distribution of cholesterol for patients in this group is approximately normal with mean mu? All right, so first of all, what we need to do is we need to set it at the claim, okay? So they're claiming that it is going to lower it, which means that it is basically 150, and we want to see if we have evidence that it is less than 150, okay? So we're going to run it at equals 150, and the average is less than 150. Notice that it is equals, okay? It is mu, not x bar, and mu less than. So we're running a one-sided test to see what's going on. All right, the appropriate degrees of freedom in this test are n minus 1. They said that we collected 28, so it would be 27. Based on the data, the value of the one sample statistic is, all right, here we go. Now we're going to enter in all the stuff. So we're going to a hypothesis test, okay, based on the data they gave us here. We're going to do a test on mean. The null was 150, okay, our sample x bar was 143, the S of x is 21, and the sample size was 28. We're going to do a t-test because we do not, this S value is not of the population, it is of the sample. All right, so here are our values. The test statistic t is negative 1.76. There we go. Okay. All right, next, the p-value is for the one sample t-test is 0.044. So larger than 0.1, between 0.1 and 0.05. So technically the p-value equals 0.045. Okay, so it is greater, let's see, it's definitely not this. It's between 0.01 and 0.05. No, it's between 0.025 and 0.05. Yes. Okay, there we go. All right, next, suppose the mean and standard deviation obtained were based on the sample of 10 patients. Rather than 28, the p-value would be what? Okay, the mean and standard deviation sample of 10 patients rather than 28, the p-value would be larger. Okay, so let's run it and let's just see. We're going to compare it. So let's say we didn't know. All right, so if I run, all right, let's try it. Okay, so if I go back to the hypothesis test on a mean, the null was 150, the sample was 143 with a standard deviation of 21. Now we decrease the sample size down to 10 and run it as a t-test, and we're going to see that the p-value is much greater. All right, we had one more question related to these right here. Okay, it says a 95% confidence interval for the average blood with similar patients who have been on a diet for 6 months is what? Okay, so if you do the exact same thing and run it as a confidence interval, so I'm going to go back to confidence interval 4. We're going to do a t-test on mean. The n was 28. All right, the x bar was 143. It's 21 for the standard deviation. Confidence level is 95. And here's our data, bang. And so we have our 143 plus or minus the error of 8.14, okay? So that is here. All right. Next, use the following to answer questions 25 to 26. We wish to see if on average traffic is moving at the posted speed limit of 65 hours along the certain stretch of Interstate 70 on each of 4 randomly selected days. A random selected car is timed and the speed of the car is recorded. The speeds are 70, 65, 70, and 75. Okay, assuming that the speeds are normally distributed, we test whether on average traffic is moving at 65 by testing these hypotheses. It is 65, it is not 65. Got it. All right. Based on the data, the value of the one sample t statistic is what? All right. So in this case, we have data. So I'm going to clear out what I have here, and I'm just going to put in 70, 65, 70, and 75. Okay, I could run basic stats. This is definitely a sample where we do not know the standard deviation. It was not given to us. Or I could just run from the app. I could go to the hypothesis test. Okay, and I could run, I guess it's not here. Let's run basic stats. So I'm going to exit out of that. Basic stats on L1. There we go. Okay, so in this case, I have an N of 4. I have an X bar of 70. S of X equals 4.08. And if I want to do the S of X divided by the square root of N, that is 2.04. Okay, so now that I have those, I can run the different portion of the app.
Please come to the office, Mackenzie Saygraves.
So now I'm going to run the hypothesis test on a mean. The null mean was 65.
Ben Van Nord, please come to the office.
Sample 70.
Ben Van Nord, please come to the office.
Okay, and the N was 4. And this would be a t-test because we're working with a sample standard deviation. All right, so we ended up with the same value we had before. Our t-value in this case is 2.45. Okay, so our p-value, we have to use the double p-value because it is a two-sided test, which is 0.09. Okay, all right, so the t statistic is 2.04. I'm sorry, 2.45. All right, and at the, it says we would reject it at the, and we would only reject this for any value greater than 9%, which would be 10%, but not at the 5. There we go.